Thank you. And I'd like to introduce our next speaker, Jeffrey West from Moffitt. Is going to talk about very cool considerations for, okay, well, I can introduce these things, but let's, okay, sorry.
All right, great. Good afternoon, everyone. Broadly, I'm interested in treatment scheduling and building math models of predicting optimal treatment schedules. And I thought I'd start my talk by casting it in the framework of adaptive therapy, especially after all the great sessions that we had talking about that yesterday and today. So we recently published this paper in eLife that describes some open questions in math models of adaptive therapy. And many of the authors of that paper are in this room, and I encourage you to read it. And it represents somewhat of a consensus statement of where we might go and what questions we might answer with these models in the near future. One of those questions that's really important to me is determining the optimal adaptive treatment scheduling protocol. So if we look at, for example, the prostate cancer adaptive therapy trial, there's two important differences that stick out in my mind. First of all, you can see the adaptive patients on the top right here receive overall a less cumulative dose compared to the contemporaneous cohort, and it's a very personalized treatment schedule. So each of those on-off periods is highly variable between patients. You might ask which of those is most important. How would we even answer that question to determine which is more important, the cumulative dose change or the treatment personalization? And related to that, should we implement dose modulation or dose skipping algorithms? Something that looks like the top or something that looks like the bottom? To do that, what I'm going to use is something called anti-fragile theory, which I found out about from where else but Twitter, where I found this example of this Wired article magazine was retweeted by a popular author, Nassim Taleb, who described the importance of this adaptive therapy trial, but using different language than I'm used to. He said, well, this is just nothing other than second order effects in medicine, to which I said, what's that? And I looked into some of his books, and one of the books he wrote was called Anti-Fragile. And he had actually written a preprint describing some of these mathematical ideas and how to bring them into medicine in general. So that was the starting point for me that made me realize if we want to answer that question, what's the most important difference, the cumulative dose or the degree of personalization? That's a complicated question, but maybe we can answer a simpler question first. An easier goal would be to classify treatment schedules by their dose mean, X bar, which is related to the cumulative dose, right, your average dose. And separately from that, we can optimize the variance of dosing in these treatment schedules. So coming up with the simplest possible example of fixed treatment schedules where we have a very low dose variance schedule of an even dosing, the same dose given every single treatment decision time point, where the variance of dosing is very narrow, right? And we could compare that to a high-low intermittent type dosing where we have a bimodal distribution of doses delivered with a high variance. And what I learned from that convex responses in medicine preprint from Taleb was that the prediction between these two, figuring out which is optimal, can be determined by our dose response curve. So in this simple cartoon, you can see that we have a dose response curve in blue, and we put a purple dot representing the response to the purple dose. And we're going to compare that response to a little bit higher dose and a little bit lower dose. And the average of those two is seen in the green dot. So if the dose response curve is convex, it's curving downwards. If we want to minimize tumor, then we should use the purple dosing schedule. But the opposite might be true. We might have a dose response curve that looks like this. And in this case, the green treatment schedule would optimize tumor regression. So we can look at the curvature of our dose response curve and determine which of these two is optimal. Okay, so let's put this into practice. And working with Andre's lab, we did some experiments where we had two cohorts of mice. The first cohort was given a high dose where we gave the green schedule and the purple schedule. And then the second cohort was given a lower dose. So in total, we have 4 different groups, and those 4 different groups are given ALK inhibitors in a non-small cell lung cancer model. So we could plot the dose response curve for these mice, and you might notice that it's curving downwards. It's a concave dose response curve. And this is an in vivo dose response curve of these mice actually receiving this ALK inhibitor. And so our prediction based on convexity, what I just told you, is that the even dosing schedule should be the best case scenario. So does that work? Well, we can see on the top, the high dose cohort, that purple dosing schedule does look to be the best. And in the low dose cohort, there's some overlap. So that gave us some indication that maybe there's something more going on here, and we should construct a mathematical model to understand the underlying dynamics a little bit more. Okay, so what is the math model that we used? This is from one of my all-time favorite papers where they describe a simple 2-cell state model which recapitulates a dose response curve. So the 2 cell states in the model are an unaffected cell state and an affected cell state affected by the drug dose. If we give no drug, we'd expect all the cells in the tumor to be unaffected, and you see that you have a net growth rate of B1. If we were to give infinite drug, then we'd expect all of the cells to be in the affected compartment where we have that net growth rate, which would probably be a net decay rate of B2. And the switching rate is what determines the other response to dose in that range of dosing values. So that model recapitulates in its steady state a sigmoidal shaped dose response curve where the plateau is the net unaffected growth rate, and the bottom plateau is the net decay rate. And the inflection point is the ratio of the switching between those with a recovery from each dose. What's important about this is I want to know something about the dose response curve, but I also have longitudinal data from my mice experiments. So if we were to add C1 plus C2, those affected cells, we could fit our longitudinal data if we knew these parameters based on the dose response curve that I just showed in the previous slide. So we take that dose response curve, and then we try to fit that longitudinal data, which I just told you should recapitulate that progression of these mice under treatment. But it doesn't work. So what's wrong with our model? Well, first of all, it does work very well in the first week of treatment, which is where our dose response curve is defined from. But the problem is that resistance occurs gradually. So we go back to that dose response model and we add one more component, which is a dynamically changing EC50, which represents the K-on parameter in our math model. And we see that the data are fit very well with that new additional dynamic in the model. So we have our dose response curve, and then we can predict a final dose response curve at the end of the experiment. And one thing to notice here is that those 2 purple trajectories end up shifting the dose response curve more quickly than the 2 green trajectories. So the 2 green trajectories seem to maintain some level of sensitivity in that dose response curve at the final time point as predicted by our model. So we have this trade-off between maximizing our responsiveness based on our dose response, but we also have this degree of resistance that's introduced that depends on our dose response, that depends on our treatment schedule. What I've just told you in the beginning is that convex functions, we would expect the purple treatment schedule to minimize the tumor regression, but the treatment sensitivity function, which is correlated to the EC50 value, is a concave function. So we would expect the green treatment schedule to minimize the EC50. So you see this trade-off that occurs, that if we want to minimize the tumor size, we should use purple. If we want to minimize the level of resistance as quantified by EC50, we should use the green. And not only that, we can do that on a per mouse basis. So we have an individualized dose response curve for each individual mouse, and we can see the distribution of final tumor size. Purple is best, and the model predicted EC50 value, green is best in that case. And this is the individual mice fits, which is really cool because we have a prediction from the model of the full dose response for every single mouse at every single point in time. So that's really the power of this model, is that we can leverage this model to describe the response to doses that these mice haven't seen in their history. So to deal with that trade-off, the last part of this talk is going to create a hypothesis of how we might leverage both aspects of the trade-off. So what we decided to try was, maybe we can start with the purple and switch to the green, or maybe we can start with the green and switch to the purple in order to maintain sensitivity, but also reduce the tumor maximally as well. So here's our model prediction that said, basically this blue treatment schedule where we start with the uneven intermittent dosing and then switch to even dosing later is predicted to be optimally balancing those two competing effects. And then we did a validation experiment, which confirms this mathematical prediction that when we look at our mathematically predicted final tumor size after each of these 4 treatment scheduling protocols, the blue is optimal. And if we look at the final EC50 value, it's interesting to see that the purple is the worst, but all of these other 3 options maintain a fairly low predicted EC50 value. So just to sort of summarize this, I had the opportunity to write a paper with Talib following up on some of these ideas, and he is really interested in the financial applications of variability, but this concept I think really applies to biology in general, especially when looking at any threshold effects. So if you see any sort of nonlinearity in the response to an input variable, whatever we're looking at in biological systems, here it's dosing, but we could consider variability in environmental signals or variability in anything really. If we know the functional form, then we should be able to use this theory to our advantage in interventions. And I promise to apply this to adaptive therapy, as I promised in the first slide, but we only looked at fixed dosing schedules here. And in the future, what we'd like to do is apply this to adaptive-like schedules, right? So these adaptive schedules on the right could be classified as a more even dosing schedule or a more uneven, highly volatile dosing schedule. So the next step of the research program here is to see if the response to these fixed treatment schedules can predict adaptive response using these same techniques. And with that, I'd like to thank the collaborators and happy to take questions. Thank you.
So that is a really, really nice conceptual framework. I like that a lot. I want to hear more about that. But so one of the things I was wondering, I'm not so familiar with dose response curves, but in last week in Plön, I've seen a lot of dose response curves and looking at, well, susceptible cells and resistant cells, and they often seem to follow more like a hill-like geometry, right? So if I cannot draw this here, but if we picture this, and we have typically these 2 hill-like equations for susceptible and resistant cells, and they actually shifted, right? And now that would mean that we would have a convex geometry or curvature for the resistance ones at the same concentration where we have a concave geometry for the susceptible ones.
That's right.
We could actually exploit that?
Yeah, that's a brilliant point. That was actually our initial hypothesis. I removed that slide, but we hypothesized that resistant cell lines would be in a concave region, more likely at least. And so you might be able to differentially select for resensitization based on your dosing scheme. Yeah, one caveat to that is, a lot of the dose response curves we see are either in vitro or they're plotted on a log scale. So that these details and nuances definitely matter. And what we've done to kind of mitigate around that is this dose response shown here was actually in vivo, which is an important consideration, I think. So I don't know how to map from in vitro to in vivo dose response, but we'll see.
Don't ask me.
Great question.
Thank you.
Cool.
Hey, I really enjoyed the story. I wonder, so the uneven schedule, it seems to, earlier we talked about how high doses might lead to more toxicity for the animal or the patient. Can you price that into your model, or have you thought about that in some context? Have you looked at it in the mice?
Yeah, it's a great question. One thing that we went back is try to look at trials where these two options have been tried, basically. And it seems like in some cases, right, you can get away with a higher dose as long as you follow it with a treatment holiday, right? So I'm guessing that's not true in all cases, but in a way that could be a way to mitigate toxicity is by when you increase the dose, you give a holiday afterwards, right? Yeah.
Cool.
Yeah. Great question.